I'll focus on topics for macromolecular crystallographers. And before I start, I was asked to show a photo of me, so that's me. And as already mentioned, I've done my PhD with Shallick about new approaches on macromolecular structure determination. And this is what basically qualifies me to talk about SHELX today. But after a short interlude in the group that developed Phaser at the University of Cambridge, I'm now with Gareb Mushadov and Rob Nichols and Paul Emsley and Fei Long, who developed RefMac and Coot and Bulbus and ProSmart. So I'll have one slide about SHELX because most people use other programs to refine their macromolecular structures. And SHELX is really very apt to do it only at high resolution. However, there are some new features in SHELX 2013 which might be interesting for macromolecular crystallographers as well, such as the multiprocessor capability, which has been there for a while on a beta test version basis. There's an enhanced rigid bond restraint named RIGU, which has been part of my work in particular, and which will possibly trickle down to other refinement programs as well. There's an ADP constraint XNPD, which such a constraint has been for a long time in Phoenix Refine and RefMac, and now SHELX can also keep ADPs from getting negative, which is particularly in protein structures a problem. We can do neutron data refinement, and actually Tim Grüne and Anna Lüben have refined neutron protein structure with SHELX. So now all the structure factors are in. There's a new way to calculate the estimated standard deviations. This is possibly for small molecule people. The flag parameter is now calculated by the Parsons quotient method. So absolute structure can be determined from an even weaker anomalous signal. However, as a protein crystallographer, you possibly have not to bother about this. And there's now CIF compatibility with the core CIF version 243. And SHELX files are embedded into the CIF that is deposited for the small molecule database so that you can easily rerun the refinement once you get to, for example, review an article and the CIF file is distributed to you. However, the main topic of my talk today will be about solving the phase problem with SHELX. So if you imagine your data, for each reflection, there's a structure factor, FHKL, and you know the amplitude approximately from the reflection intensity because they're proportional. And the phase of that structure factor is unknown. So for each and every reflection, there's a structure factor, you know the amplitude, but you don't know the phase. And that constitutes the central problem of crystallography, the phase problem. Every experimental phasing method exploits differences in the measured intensities that are caused by some kind of marker atom. So in SIR or MIR, that might be soaked in heavy atoms. In SAD, that might be native sulfur or in selenium-methionine. In RIP, radiation-induced, damage-induced methods, that might be atoms that have been removed or partly removed by the radiation damage. But in every experimental phasing method, there are marker atoms, and finding them first and using the difference they cause in intensity is the goal of these phasing methods. And SHELX CDE is a software package for experimental phasing, and it uses this kind of abstraction of all the experimental phasing methods to treat them at least similar. And I'll go shortly into the theory behind that, which is kind of the SHELX view on things. So we use something we call the alpha angle. If you have your overall structure factor for a reflection in the complex plane, so you have an imaginary part here and a real part of the complex number here. And this structure factor F total has a phase called phi total, which is this angle. You can regard this structure factor Ft as composed of two structure factors. One of them is Fp, the contribution from the protein, and one of them is Fa, which is the contribution of your marker atoms. A here stands for atoms or anomalous scatterers. And this Fa contribution will also have a phase angle, and that phase angle will differ from the total phase angle. Now, the alpha angle is actually the difference between the total phase angle and the phase angle that is assumed by only the contribution from the marker atoms. So in a set experiments from the anomalous scattering, or in a mere experiment from the soaked in heavy atoms. So the theory behind this is that if we know the phase contribution from the marker atoms, and we know the alpha angle because we can estimate or calculate it by some means, we can get the total phase, and consequently for the structure factor have solved our phase problem. So the individual programs in SHELX-CDE are SHELX-C, and SHELX-C will calculate or estimate the alpha angle based on your experimental data, and it will also prepare your files. So your experimental data go into SHELX-C, and then out come the prepared files. This file will actually contain the alpha angles. SHELX-D searches for the positions of the marker atoms, does the substructure search, and it puts out a potential substructure of marker atoms, so it gives you marker atom positions. SHELX-E does density modification and phase improvement to actually improve the initial phases that were gained by those calculations. And all maps and coordinate files that are output by these programs are compatible with code and can be read into code. This is, by the way, the main SHELX citation you should use. So SHELX-C calculates or estimates the alpha angle, and it also does some data analysis. SHELX-D is originally for the ab initio phasing of big small molecules, so it wasn't intended for experimental phasing of proteins. It was intended for ab initio direct methods phasing of, for example, peptides, and it uses Patterson seeding and dual space direct methods. So Patterson seeding means it starts with atom positions that are already consistent with the Patterson you can calculate from your reflection data, which is a much better starting point than just random atom positions. And dual space direct methods means that the positions of the atoms are both evaluated in real and in reciprocal space, and that leads to a much faster convergence. Once you have done that and it has converged, you have a substructure that is determined, one that is really looking very good, and you and the program think you should keep it. You have this phi A angle. From SHELX-C, you have the alpha angle. So you end up with phi T, the so-called initial phases. These initial phases go into SHELX-E, which improves the initial phases by density modification with a so-called sphere of influence algorithm. I'll explain in the next slide how the sphere of influence algorithm actually works. This resolves the handedness of the substructure. It is very important to recognize that you have not resolved the handedness of the substructure by finding it in SHELX-D. You don't know which enantiomer you actually have before you have done density modification. It can't be stressed enough that you actually have to try both hands. SHELX-E can also be employed to use the free lunch algorithm for nucleic acids and mid to low resolution data. So we have a new thing, I'll talk about it in a few slides, which is autotracing. However, autotracing is not feasible for nucleic acids at the moment, and it's not feasible at resolutions worse than 2.5 angstrom. And in such cases, you still want to use free lunch, while at better resolutions, it is more of a cosmetic thing to use. So density modification with the sphere of influence algorithm. Density modification generally exploits the fact that some part of your structure will always look like solvent, while other parts of your structure will look like protein, and those two are distinctively different. Solvent areas, disordered solvent areas, exploit a relatively uniform electron density with not much variation, while protein-occupied areas will show peaks and holes. And that is exploited, and the map is modified in a way that the solvent areas get flatter and protein areas become sharper. SHELX does it like this. So you have your map calculated with the initial phases you got and your native normal data. So you have an initial map. And for one position inside the map, you ask yourself, is that an atomic position? Am I actually inside my protein? So around this position, you draw a sphere. That sphere has a radius of 2.42 angstrom. Now, 2.42 angstrom is the typical 1-3 distance in a protein. So if the point in the middle was actually an atomic position, somewhere on that sphere, there should be another atom. You plot the electron density on the surface of the sphere, and you look how much it varies. Now, if it doesn't vary very much, you obviously weren't inside the protein, you were somewhere in the disordered solvent area. So you flip the density, because the density is later combined with a similar density, it will end up to be 0 in the course of several iterations. The alternative is the density on the surface of the sphere varies a lot. In this case, you want to sharpen the density because you think you're actually sitting on an atomic position, and you should sharpen whatever is around you. This, in time, leads to a relatively good map and reduces the phase error. So there are several new features in the new version of SHELX-CDE. I'll give them together with some practical guidelines. SHELX-C can now read input data in various file formats, HKL, SCA, and XDS ASCII.HKL format. So there's less converting necessary. You have improved statistics for low resolution data, and there are now also checks for consistent indexing. This, of course, is not necessary in a SAT case where you only have one data set. But if you are doing a MED experiment where you have a number of data sets and you are in a space group where you can have different origins, you want to check for consistent indexing. In this case, the program will give you a warning and will reindex if necessary. SHELX-D now uses multiple CPUs, which has been, with the beta test version, put to use in a number of synchrotron beamlines. It's really much quicker now. We routinely run several 10,000 of trials when we are searching for a substructure, and sometimes just waiting long enough and running enough trials is getting you there. Also, the Patterson seeding is faster and can now also be employed without hesitation in cubic space groups. Critical factors in the substructure search with SHELX-D are: the number of marker atoms you specify as input should be correct within 30%. The resolution cutoff of the data is very important. You want to cut your data there where the signal of your marker atom, so in SAT, for example, the anomalous signal, stops. However, if you have a problematic case, I would recommend that you try several cutoffs, because the cutoff can really determine whether the structure solves or not. And the data have to be scaled properly, and the data quality has to be good. You can imagine methods like SAT use the difference between Friedel mates, and if one of the Friedel mates is obscured by a beam stop and hasn't been thrown out at integration, the difference that results from this will be huge and will dominate all of the substructure search. So properly process data that have been properly scaled are really crucial. Also, SHELX will now automatically do all the programs will now do automatical anisotropic scaling. As an indication of the correct solution, there is the best C-form, which is directly given in the command line output. Or if you use a GUI like HKL2map, a sharp drop in occupancy, and a high CC all and CC weak value for that particular solution, very distinct from a cluster of non-solutions, give you usually a good idea. However, if you're unsure whether you have solved or not solved the structure with this substructure, you should just proceed to SHELX-E. It may give you a clearer indication. SHELX-E now can do auto tracing, and this is the result you can expect for a high-resolution structure from the auto tracing. So you can clearly see that this map doesn't suffer very much from phase error, and you can even see ring systems. So this is a beautiful map, and every one of us would love to build in it. However, it is very important to keep in mind that the polyalanine backbone auto tracing employed by SHELX-E is there to get the best experimentally phased map. This is the main purpose. A byproduct is that you get a polyalanine trace that can be used as an input for a Bohr, Buccaneer, Resolve, or Main. So this is not a tracing program. It's a density modification program, and we try to get you the best phases. It's very important to say that please use a program for automatic model building if you want to do automatic model building. However, we found out that the structure traced is a structure solved, and that is very, very, very handy. If the CC of the partial structure, which is traced against the native data, has exceeded 25%, and if you are at a resolution better than 2.5 angstrom, the structure has been solved. We haven't found empirically any exception to this rule so far. There's also a new facility in there, which is the marker atom substructure optimization, which can be used at any resolution. So this is not at good resolution, can be used at any resolution. You specify -z in the command line, and the program will optimize the substructure against the data. So recycling substructures through SHELX-E is hopefully no longer necessary. Also, SHELX-E now has new MR and MRZ facilities, about which I'll talk later. I'll first give an example, and that example is fibronectin. The structure was originally solved by RIP because sulfur Z was not feasible at the time alone. It has 1.51 angstrom resolution, 4 disulfides, 2 methanines, and some sulfate. SHELX-2013 can be used to do sulfur Z for this structure. It's very important to cut off the resolution at a specific threshold where actually the signal ends, and that the disulfide peak search with the dsol command has to be used. This peak search command is in particular there for disulfides and search for elongated peaks in the difference map. Now, then if we run SHELX-D already in trial 35, we get good CC values. However, if we wait just 2 minutes longer with the multiprocessor version, in trial 1452, we get much better solution that is almost entirely correct. If we then run SHELX-E 2013 as a standard sulfur Z density modification, we get a mean phase error of 53 degrees. However, if we employ auto tracing as well to improve the density modification, we get a much lower mean phase error, and it can be taken for relatively sure that this map will be much nicer to build in than that one. So the auto tracing really improves the phases here. This is an image of SHELX-E processing. So SHELX-E auto tracing runs in macro cycles. There is density modification, 20 cycles, then comes an auto tracing cycle, density modification, next auto tracing cycle, density modification, last auto tracing cycle, and then another density modification. The colors here refer to the RMS deviation between the real structure and the trace. Red is wrong, so absolutely incorrectly traced C alphas are listed here. And what we can see in the first autotracing cycle, almost nothing of the structure is entirely correct. However, over the course of the density modification and autotracing, things improve hugely. So this means there was a relatively small toe hole to start from with the substructure because the signal was weak, but the density modification and autotracing actually can improve it to a relatively complete structure. The second example is about MR and SHELX-E. It's the structure 1ZZK. Input phases from SHELX-E can be from a molecular replacement model. To improve the map quality beyond the MR model. So you can use it if you have a molecular replacement solution, you're not sure of it or it's problematic to refine from. You can improve your phases with it. You can improve the map quality beyond the MR model. You can reduce your model bias, but you need data better than 2.1 angstrom. So this is really only feasible at high resolution. And there will be very soon an article about this in Acta Christi. What you do is you take your name.hkl, which are your native data, so you don't need any experimental phase information, and you take your MR solution renamed to PDA instead of PDB. You drop it into SHELX-E and do autotracing, and what you get should be a map that hopefully looks nicer. You can also employ SAT data in addition to the MR data to do MR SAT, to bootstrap weak SAT signals with an MR solution. In this case, you put your SAT data into SHELX-C as if you wanted to do experimental phasing. However, you skip the SHELX-D test, the SHELX-D step, because actually the MR solution is going to provide initial phases. You drop both in SHELX-E together with the native HKL file, and hopefully you can autotrace your structure again. This is very feasible up to 2.5 angstrom resolution because actually your phase information comes from more than one source. So this is an example of pure molecular replacement with SHELX-E. So you have a molecular replacement solution which is from Phaser and has actually been generated by the pipeline AMPLE, which uses ab initio models, and the data have been given to me by Ronan Keegan, who has done this research. So it's a very nice example. I'm very grateful that he gave it to me. The translation function z-score, which in Phaser is a measure of how confident we are in the solution and also the LLG, is not particularly good. From this, you wouldn't be able to tell that this is actually a solution. Actually, the placed fragment is also very small. It's only 4 residues for a roughly 100 residue protein. However, if we put this into SHELX-E, we get a structure like this. And as you can see, this is 86 residues, so it's almost the entire structure. The correlation coefficient of this trace against the native data is 32%, meaning it's over 25, so the 25% rule applies, and we can be very, very certain that this structure is actually solved. Besides that, in COOT, of course, you are well able to see the side chains. So what does this mean? Fragments can be very small if they are placed correctly by the MR program. And this is exploited in pipelines, such as Archimboldo, which is developed by Isabelle and Son, to whom I'm also very grateful for examples and lots of teaching. AMPLE and Autorickshaw, which was actually the first program to employ this. SHELX-E can give you a quick indication of a correct MR solution, as it needs no sequence, and consequently it can be a step in between automated MR and complete auto-building. However, it is very important to keep in mind that those structures that aren't, so there's those MR solutions that aren't solving with SHELX-E that don't get a CC better than 25% are not necessarily wrong. So you can't turn that around. I'll give quickly 2 slides about Anode. Anode calculates anomalous or heavy atom density. And if SHELX has been run, the input is straightforward. The program is distributed together with SHELX. However, it's not a program to solve the phase problem. It's rather there for validation or to look at radiation damage-induced reactions and structures. So we had this equation in the very beginning, but now we've turned it around. Given that we already have a PDB model, a partly refined structure, for example, or a final structure, we can get phi total. We have the alpha angle because Shallick-C estimated it for us in the beginning of the phasing. So then we can calculate phi A, and we can actually calculate it a little bit better than with Shallick-C because the PDB model should yield us better phases than we got before. We can use these phases and combine them with whatever differences we have used for phasing. So for example, this can be from a SAT data set at a long wavelength, where we get an anomalous signal, in which case these would be the anomalous differences between the Friedel mates. Or in a SIR case, it could be the differences between two data sets. Or in a RIP case, it could be the difference between a data set taken before the radiation damage and a data set taken after the radiation damage. However, if we calculate a map with it, such a map is called a difference map, an anomalous difference map, or a heavy atom density map, or a radiation damage map. And such maps are usually giving us good indications on atoms. So this is just one short example. I'm not showing any radiation damage examples or anything else, but information can be found on my homepage. This is a structure of viscotoxin, and this viscotoxin couldn't be solved by SAT because the signal was too weak. But actually, a node reveals that there was enough signal in the data to spot all the disulfides. We are just not yet technically able to exploit it. You can see all the disulfide bonds beautifully. The resolution is 1.5 angstrom, so it's a brilliantly good resolution. You can even see sulfates. However, there's one sulfate here, and actually I would argue with that being fully occupied. It seems like the sulfate is only very partly occupied, and a node can be used to give you such an indication, or to give you an indication of what reactions happened with radiation damage, or if you are looking at MAT data at the identity of metal ions. To sum it up, new features in SHELX-2013. So there's a lot, but the most important in my opinion are SHELX-L Rigo, multiprocessor capability, and SIF output. In SHELX-D, the multiprocessor capability, which allows now for a lot more tries to search for the substructure. Autotracing in SHELX-E, which allows much better initial phases for refinement. And molecular replacement functionality that allows for the combination of phase information from different sources. Or to use SHELX-E to improve your molecular replacement solution without any experimental data. And the small tool Anode to visualize anomalous heavy atom or radiation damage density. SHELX, besides from SB Grid, is also available free for academic use from our homepage. Under the same domain, my own homepage can be found. And the new version replaces all previous beta versions, so please make sure that you have updated to SHELX-2013 for all other programs to run well with it. This is a final distribution of Shallick, and no beta versions should be kept. So, and thank you for your attention this morning.
Thank you, Andrea, for your very interesting talk. If you have questions, you can chat them to me by the chat window, which is, if you're using the Fuse clients, that little sort of thought balloon or speaking balloon. So I haven't seen any questions come through, but we'll give it a minute or two to see if anybody has any questions. So that doesn't seem to be the case. I'd like to remind everybody that we will be posting this webinar on the SB Grid TV YouTube channel. So I guess that'll be it, unless there are any final questions at the last moment. I did see the question that just came around that said somebody asked if SHELX-2013 is in the SB Grid release, and I'd like to say it is. I don't remember exactly when it went in, but it is there now, so it should be all set for people to use. Okay, it seems like we're all set. So thank you again, Andrea, and thank you everyone for attending.
Yeah, thank you.